Today, we're presented with a seemingly simple task, finding 3 consecutive odd numbers within an array. The challenge isn't just to find them, but to do so efficiently. How would you approach this problem to ensure optimal performance? The problem asks us to determine if an array of integers contains at least 3 consecutive odd numbers. We're given an integer array as input. Our output should be a Boolean, true if such a sequence exists, false otherwise. We need to identify if there's any triplet of numbers, say at index I plus 1, and I plus 2, where all 3 are odd. A straightforward brute force approach involves iterating through the array and, for each element, checking if it and the next 2 elements are all odd. We'd start checking from the first element up to the third to last element to ensure we always have 3 elements to compare. This means a loop running from index 0 up to array length -3. Inside the loop, we perform 3 modulo operations and a logical AND. If all 3 are odd, we immediately return true. While simple, this method repeatedly checks elements that have already been part of a previous triplet check. This approach runs in big O of n time and uses big O of 1, constant time space. The key insight for optimization is that we don't need to recheck previous elements. We can use a sliding window concept, maintaining a count of consecutive odd numbers. As we iterate through the array, if we encounter an odd number, we increment our counter. If the counter reaches 3, we've found our sequence and can return true. Crucially, if we encounter an even number, it breaks any current sequence of odd numbers, so we reset our counter back to 0. This single-pass approach avoids redundant checks by maintaining state about the current streak of odd numbers. It's a classic example of how to optimize sequential checks by leveraging information from the previous step. Let's trace this with an example array, 2, 6, 4, 1. We initialize a count variable to 0. The first number is 2, which is even. So, count remains 0. Next, 6, also even, count stays 0. Then 4, again even, count is still 0. Now we encounter 1. 1 is odd, so we increment count to 1. Since count is not yet 3, we continue. The array ends. We never reached a count of 3. Therefore, the function would return false. Consider another example, 1, 3, 5, 2. 1 is odd, count becomes 1. 3 is odd, count becomes 2. 5 is odd, count becomes 3. At this point, we immediately return true, without needing to check any further elements in the array. For our example array of 2, 6, 4, 1, the final output is false. This is correct because, as we traced, there were no 3 consecutive odd numbers present within the sequence. You'll spot this pattern when the problem asks you to find a sequence or a subarray that meets a specific condition, especially when that condition depends on the immediate preceding elements. It's a strong signal for a sliding window or a state tracking approach, where you can update your current state based on the new element without reevaluating the entire window. This optimized approach runs in big O of n time because we iterate through the array once. The space complexity is big O of 1, constant time, as we only use a single counter variable. This pattern is highly applicable to many array-based problems. Try the next problem, which involves finding the maximum sum subarray, using a similar sliding window mindset. Don't forget to like and subscribe for more DSA insights.